Well, thanks, Alistair, and I'd like to extend a welcome to all of you that have made it here today. So I think most of you would know me. I'm Martin Green. As well as my job here at SPREE, I'm also Director of the Australian Centre for Advanced Photovoltaics. That involves 4 other universities and a division of CSIRO. So the research arm extends a little bit broader than UNSW. So what I want to talk about today is just some of my ideas on where the solar industry is heading. So it's been a big year, as Alistair mentioned, for solar. We've seen quite massive reductions in cost as reflected by the sort of real world bids for solar, for supply of long-term electricity from solar. So these are record prices that we've seen for auction bids for the long-term supply of electricity. So the red line there just shows the bids that have been made over the last 4 years for solar supply in different countries. So it started off quite high. The dashed lines, the horizontal dashed lines just show the record bids for other forms of energy, just to give you a benchmark. So you can see geothermal, relatively expensive, and new coal plant, gas, wind is one of the cheaper ones. But solar's moved over the last 4 years from being one of the more expensive options to being now the cheapest option. So last year in 2016, we saw solar get below $30 US a megawatt hour, 3 cents a kilowatt hour for the first time. And then just recently this year, we've seen it get below $20 a megawatt hour, 2 cents a kilowatt hour. Now, I think it's almost certain that we'll see it get below $10 a megawatt hour, which is just an outstandingly low price. So that's 1 cent a kilowatt hour. So I'm not sure exactly how they managed to put these systems together for that type of price, but this is what they're bidding on, and hopefully not losing money. So the really interesting thing is, the latest bids, the bids are coming in about a third the cost of the bids that come in for new coal-fired electricity from, generated by a new coal-fired plant. So that bid was in Chile, but, it was $57 a megawatt hour, and the solar's coming in at $17.86, I think is the lowest bid that's been made so far for the solar, so about a third. So really a new era. And Alistair mentioned that solar's now lower than just the cost of the gas for a gas-fired station. Well, the same is happening internationally for coal. So the grey dotted line there is the opportunity cost of coal. So that's just the value of the coal at $60 a tonne. The amount that you'd have to burn to generate a megawatt hour, that's the value there. So the solar is now undercutting that. So quite a new era. The spot price of thermal coal is now 97 US. So this is doing a bit of an underestimate of what the opportunity cost is. So cost very cheap and getting cheaper. So opening up new opportunities for solar. This is my take on the learning curve. So, well, it wasn't really me, it was CITI Research who first published this, but this just plots the price of a solar module, dollars per watt on a logarithmic scale versus the cumulative capacity. So normally people fit one straight line to this and get a learning rate of about 22%. So that means every doubling of production, you get a 22% reduction in cost. But the Citigroup sort of tried for a more sophisticated analysis and divided into 3 portions. So an experimental phase where you're just sort of fiddling around really, but quite a high learning rate associated with that of 33%. And then what they call an industry development phase where the industry started taking off, but a lot of teething problems to get the industry up to scale. So things like shortages in polysilicon as the industry sort of worked out how to supply that in the volume needed and so on. So a slower learning rate associated with that. And now with all that sorted, we're in the mass production stage where you can really, bite the bullet and get the costs down low very quickly. But if you look at the way the costs have decreased over the past few years, it's more like a 40% learning rate. So really very massive reduction in the cost for, every bit of extra generation. So, last month the average selling price according to PV Insider's report was 33 US cents a watt. That's the average wholesale selling price of a module. So really massive decrease. So I calculated in 2016 the costs decreased by about 20%. This year looks like about a 30% reduction. So really very rapid reduction in cost. This was a very important forecast made by Bloomberg in 2015. So it was one of the first groups with any credibility to just point out, what a large role photovoltaics was going to play in the future, and I think it was quite important in changing perceptions about the possible role of photovoltaics. So this is just projection of new electricity generation capacity out to 2040 with the yellow regions solar, small scale and utility scale solar, gradually taking over as the majority of new electricity production and completely dominating things by 2040. So although very important, it was also very conservative. So over the period, the 2 years since that was prepared, they were projecting a 24% growth in production. The actual growth's been 85%. So even though this looks quite overwhelming in terms of the amount of solar projected, it's probably a huge underestimate of the impact that solar is likely to have upon electricity generation. So there's been some more recent studies. So there was an article in Nature Energy, and I'm not quite sure of the methodology they used, but they came up with some enhanced projections. So what this shows is total installed capacity versus date. And the green and brown areas there are just a number of other forecasts that have been made. And the Bloomberg forecast is shown there, like middle of the road type of traditional forecast. But their calculations, I couldn't quite understand the methodology they were using, but it came out with results. It was projecting the brown lines you can see there, depended upon the costs that you could, where photovoltaic costs eventually bottomed out. So if it got down to half the present cost, which I think is almost certain, you got the lower line and then a quarter the middle line, and if there was no limit, the cost just kept decreasing as the learning went on. You got the top line. So much higher projections than previous. And I think this is more in line with my own thinking. Now the costs of solar are so cheap. Why is suddenly the growth rate going to slow down? The grey areas show a continuation of the exponential growth that we've seen over the last 20 years. So if you work out the average compounded growth rate over the last 20 years, it does come to 40%. So we've had 40% compounded growth over that period. So those grey lines show what you'd expect if that rate continued. One side, the low capacity side, is 18% compounded growth rate, so exponential growth continuing, and the high capacity side is 50% growth rate, which is not all that much higher than the 40% we've actually been seeing. So the idea, I guess, that's starting to gain traction is, this exponential growth will continue for a while and then we'll flatten out into a linear growth or constant production volume regime soon after. So the opinions are varying about when that transition might occur. Been some interesting studies by a Finnish university, LUT, now the full name's down the bottom there, Lappeenranta University of Technology in Finland, where Christian Breyer, who used to work at Q-Cells, has moved to. So he's been doing he's done a very detailed study of the uptake in photovoltaics, and he gets quite similar results to the high level one that is shown there. So his correspond to, over 20% compounded growth for the next few years out to, well, the next 13 years out to 2030, and then switching to a linear type of growth mode there. So I think we'll see more of these forecasts trying to grapple with the idea of, with this new era of solar with a very low costs, what's that mean for the future of electricity supply? I think we're going to see much more optimistic forecasts than what we've seen in the past. And why is this important? And it's all to do with the CO2 emissions. So this is a graph I found very influential in my thinking, but it shows actual CO2 emissions, global CO2 emissions to 2014. That's the black line at the top. And then one of the projected trajectories of what you'd have to do to keep global temperature rise below 2 degrees centigrade. And you can see that there's a big problem coming up in the not too distant future, in that if you look at the best efforts of the 4 biggest polluters, by 2030 you run into a problem where they've used the whole budget for a 2 degree centigrade sort of, to keep temperature rise to 2 degrees centigrade. So it really needs some drastic action. This graph was actually drawn in 2015 when PV costs were really very high, but now with the reduced costs, I think there's a chance we can really address the CO2 emission issue through photovoltaic uptake. So as I mentioned, the industry's been growing at compounded growth of 40% a year for the last 20 years. So if we can keep that growth rate going a little bit longer, to 2025, we'd then be producing over 1 terawatt of photovoltaics a year. It looks like this year it's going to be over 100 gigawatts or 1/10 of a terawatt. So another 7 years, you get to a full terawatt at that growth rate. And the importance of that is that if you look at the impact that'll have upon greenhouse gas emissions, if you're displacing coal from electricity generation or oil from transport, it's roughly the same. That's the impact you'd have on CO2 emissions. So if you're putting in 1 terawatt a year, you can reduce the total emissions at a rate that's faster than the 2 degrees centigrade rate there. And if you can do it by 2025, kick in at this terawatt level, you can do it on the sort of right type of timescale. So for the first time, it looks like PV may provide there's many grounds for believing PV can provide a technical solution to keeping greenhouse gas emissions under control. Yeah, just looking at the source of greenhouse gas emissions, this is a graph from ARENA, but the brown region you can see there is electricity generation, so it's overwhelmingly the biggest source. So according to ARENA, it's close to 40% of the total greenhouse gas emissions. So doing things to enhance the installation of photovoltaics at both small and large scale is going to be important to decreasing the size of that chunk, displacing coal generation electricity in particular. So I guess that's where our PERC technology comes in. It's becoming the technology of choice within the industry, with most new capacity now PERC capacity. This just shows the history of our cell development in our labs here, but the headline sort of figure is we've held the record for the silicon cell efficiency for 30 of the last 34 years, and we increased the performance by 50% relative with that PERC structure, the outcome of it. This is just the roadmap, the last published roadmap estimate of the PERC uptake compared to the other technologies there. So the industry is moving to higher efficiency technologies. The non-PERC technologies generally involve the use of N-type wafers, so additional barrier to their adoption through the need for the industry to transition from P-type to N-type wafers. This is just a chart I think ISFH published initially, just showing the record efficiencies for commercial sized PERC cells from 2010 when commercial interest started developing to 2014. I used it in one of my talks I gave in 2015, projecting how that growth might occur, so projecting quite rapid growth of the efficiencies. If you look at what happened, it turns out it just about follows my projection exactly. So recently Jinko had a 23.45% PERC, large area PERC efficiency confirmed. So heading very much towards what we were able to do in the laboratory. If experience with some of the other technologies like the integrated back contact cell is anything to go by, once these technologies get to production, you actually reach higher efficiencies than in the lab. So in the lab, Stanford got to 22, 23% efficiency with their integrated back contact cell, whereas now SunPower is able to do over 25% efficiency. So if the same thing happens with PERC, we may see commercial efficiencies above 25 and maybe above 26% efficiency, maybe following this trajectory. But eventually you're going to run into a limit with the PERC, and some of the work that I've been involved with many researchers within our centre has been in trying to find a technology to lead you beyond PERC. What I was going to say before getting on to that was a bit of a battle between whether adapt multi-crystalline silicon or crystalline. So with the multi-crystalline you have the advantage you can go to very large ingots. So the scaling of the technology to larger ingots and so on is a bit easier with than with the Szykrowski growth that is shown at the bottom there. So a big battle within the industry now between multi and Szykrowski. I visited Longy recently and they were experimenting with growing 3 big ingots from one crucible, one silicon crucible, sort of cutting down on the material costs of growing the Szykrowski ingot. So still undetermined as to which way it would go. And if Szykrowski, if mono takes over, there's less of a barrier switching to N-type wafers. So it'd be interesting to see how all that develops. So that's just showing you some of the size. That big ingot there is a 1.2 tonne ingot that the company shown there actually made. So just showing the size things are going to get to in the future. So at some stage, they might have ingots as big as this room. Something to look forward to. Okay, so I think from my perspective, I think the 2 most important lines of research within the centre, and one is the work in the here and now of getting the PERC technology perfected in commercial production. So perfecting the production and transfer of the PERC through the hydrogenation work our group's doing, I think is one of our very important projects. And the one for the future is trying to develop a tandem cell on silicon, because I think that gives you a boost potential, another 50% boost potential. Like the PERC, with that we're able to boost the traditional or the prior cell efficiency by 50%, but there's another 50% waiting to be obtained if we can successfully develop a tandem cell approach. So that chart just shows efficiency potential, but 25% with the PERC may be what we see in production. If you can carry the same, if you can get to the same quality of processing with a multi-junction device, you may be looking at cells that are over 40%. So that's another thing to look forward to the future. So this is my concept. I think transitioning to a tandem cell would be very easy if you could build this cell on silicon, because existing manufacturers could participate in that transition. So this is my concept of how you'd make that transition, putting a thin film cell on silicon, first 1 cell and then 2 cells. So the importance of the silicon becomes less and less. Like if you put a cell on to a silicon cell, the silicon contribution to the efficiency is halved because you share the current. So you only got half the current in the cell. If you put 2 cells on, the contribution of the silicon's down to 1/3. So if you put 3 cells on, it's down to 1/4. So diminishing returns from the silicon as you put more cells on top. So my thinking is that putting 2 cells on silicon is really sensible, but by that stage the industry will have a lot of experience with the thin film technologies involved. So for a 3-cell stack you might get rid of the silicon at that stage, which may be 20 years down the track. In terms of cells to stick on top of silicon, the problem is there's been no ideal material yet identified. So some labs are getting very good results with 3-5 cells, but that's very costly processes that are involved, generally wafer bonding to bond the cells onto the silicon wafer. So some very high efficiencies being reported, but practicality is a big question mark around. So we're trying to develop a thin film cell, a polycrystalline cell that doesn't rely on a crystallographic match to the silicon. So the way you go about finding those is sort of indicated here, just sort of digging down through the periodic table to substitute, like a group 4 element for 2 and 6, and then, dividing the group 2 into a group 1 and 3 and so on. But sort of digging through the periodic table, that way we've been able to uncover several new classes of semiconductor that no one has identified before. So we've got a whole new bunch of semiconductors very similar to this CZTS material that we're already working on that we're planning to work on in the future. So we're hoping one of those has some of the advantages of CZTS without being as difficult to material to work with as CZTS is proving to be. So Zhao Jing's doing some excellent work with the CZTS. So Earlier this year got a world record with the CZTS, her team, with 11% efficiency. So where the rate of improvement with the technology has been very rapid. So the previous year, we started with 8% efficiency. So if we can keep going at that rate, we'll be up to 20% within a few years. So that's the hope with the CZTS technology. And then Anita is working with the perovskites, which is also an interesting material to stick on top of the silicon. So big issues with the stability of the perovskites, and at present you have to use lead in them, which may not be something that manufacturers are really keen to do. If they take the trouble of getting the lead out of their solders and so on, they may not wish to put the lead back in. Just to finish up talking about some of the other projects I'm interested in. If you look at the second largest single source of CO2 emissions, it's actually from passenger cars, which accounts for about 10% of CO2 emissions. And largely through the efforts of Elon Musk and Tesla, electric cars are well and truly on the agenda as a way of displacing oil from transport. So I think, without Tesla, producing such a brilliant car, we'd be several years behind in our thinking about electric vehicles. But it seems that, electric vehicles are gaining momentum as the way transport might evolve. But something quite interesting is that it turns out if you put solar cells on an electric vehicle, it can have a surprisingly large impact. So I guess we're used to solar car races, when you have these very specialised vehicles and they're not very practical in terms of the weight. We have to make the compromises with the weight and the passenger carrying ability and so on. But they have to travel 3,000 kilometres. But a normal passenger car only travels, like in Australia, the typical daily commuting distance is less than 30 kilometres. So if you look at it that slightly different perspective, you end up with a different perception of what the impact might be. So I attended a talk from Toyota earlier this year. I forget which conference was that now, but they've experimented with a Prius, which I was quite keen. I wanted to put solar cells on my Prius, but I couldn't get any undergraduates interested in taking that thesis topic on. But I was going to load my Prius up with solar cells like this and just see what I could do with it. But Toyota actually did it. So they loaded a cell with sun power cells, as indicated here. So they've got about an 800 watts generation capability from the solar array. It turns out the area of cell is 6.6 square metres, whereas the area of paint on the car is more like 10 square metres. So even though the car is heavily loaded up with cells, you can get a lot more area if you've got the whole paintwork active. And Toyota are believing they can reduce the weight of Prius. So the rating of the Prius is 8.8 kilometres per kilowatt hour, according to some Japanese rating system. But they believe they can double that by reducing the vehicle weight. And I guess the way, with driverless vehicles and everything, I guess, in the future we'll be getting to work by phoning up on our mobiles or some type of lightweight driverless pod. So you can sort of see that vehicles might become very light if they become driverless, and the probability of having a collision goes way down. You might need these sort of tons of metal to protect us. So, it is quite possible we do go much lighter in vehicles as we go to driverless vehicles. But this is the results. The blue lines just show the solar installation and the red shows the output. Because you've got solar cells on the side of the vehicle, you don't get such a big differential between summer and winter generation. This is 100 days of monitoring that covers both summer, which I guess is the first bit, and then winter towards the end there. So some reduction in winter, but not as large as the sunlight availability. So with all those panels, they generated over 2 kilowatt hours per day on average in Tokyo, driving around Tokyo, I think it was. So with this 17 kilometres, you get 36 kilometres a day. And it turns out the average commuting distance in Japan is 24 kilometres. So it really would mean that if you had a Prius that was loaded up with all those cells, you wouldn't have to go to a petrol station very often. So even with the Prius itself, I think it was 19 kilometres that you would have attained even with the standard Prius now. But this is just shows they calculated how much CO2 reduction you might expect from that. So what these little bars just show is the percentage of drivers doing different commuting distances. So the first little bar is those doing 5 to 10, and then 10 to 20, 20 to 30, and so on. So it's just, you know, so I shouldn't have been pointing with my finger, but 10 to 20, 20 to 30. So, you know, over 50% is 24, so it's somewhere in this bar here. But, you know, they calculate 36. So for this group of cars, which is most of them, I think it was 70% of the cars, you could power the average driving distance entirely by solar. And then as you got cars that did further and further distances, you'd have a bigger and bigger percentage, you know, where you'd have to use petrol to power the hybrid vehicle. But they calculated that you could reduce the transport-related CO2 emissions by 64% by just sticking solar cells on a car. So although, you know, like, that was a bit of an eye-opener to me, because before then my opinion had been influenced by solar cars. I thought, oh, it's not really practical for real-world vehicles, but that type of calculation shows it might really be. And then just 2 weeks ago, Elon Musk launched his electric semi-trailer, and look at the area you got there for solar cells. Really massive. Okay, so we've, Anita presented at Google X earlier this year, I think it was, on our ideas on solar paint. So that's an area that I've become quite interested in. So the normal way of connecting cells to build up the voltage is to connect them in series, which is, I think, is a bit too awkward for a car because of the, you know, the weird body panel shapes and the fact that, you know, as you turn corners, you get shading, you know, moving along the panel and everything. So I think, and then if you got a scratch on your car or something, you could lose the whole, you know, the output of the whole string. So having all the cells in parallel seems to be the way to go. But if you use a tandem approach, you can have, you know, a limited number of cells in series through that to get a decent voltage. You know, the problem with solar paint is, you know, if you paint something like that screen, you'd be generating, you know, like how many amps, like hundreds, thousands of amps of current. So the problem, you know, with solar paint as an idea is, you know, how do you handle the very high currents that you'd have? So I think one way of doing it would be to feed it through. So like a, you know, a metal or emitter wrap through sort of idea, feed it through the body panel through small holes or plugs in the body panel. And the idea there just sort of shows what the scheme might look like, where you feed the low voltage being generated through the cells, which is governed by a up-converter chip. It just collects current from the area where, you know, that it's servicing, and then boosts it up to a higher voltage that you can then distribute around the car or interface with your battery or something or other like that. So I'm quite interested in following some of these ideas up once you realise the impact that it could make to, you know, to transport emissions. Oh, that brings me to the end of the talk. I hope I haven't gone over my 20 minutes by too much. But yeah, so just, I think with the recent cost reductions, I think we're in a new era in thinking about PV. You know, I think the challenge now is to try and keep the industry growing at its past rates, or at least the next decade. And if we're able to do that, I think we can make a really significant impact upon CO2 emissions. And there's nothing else out there, like chance of a political solution are very remote. So there's nothing else out there that really makes sense that can really tackle that problem. There's still plenty of life left in standard silicon cells. I think we're going to see, you know, ongoing cost reductions. We're still in a 40% sort of learning rate regime with them, so still very much lower cost, which is quite astounding, the fact that you can actually make these cells so cheaply. So I think stacked cells on silicon is a sort of logical progression. So if you look at my earlier chart, it's going to take at least 3 years and probably 5 years for commercial PERC or PERC cells made by commercial manufacturers to get to this 25, 26% level. So then the whole industry will be looking for some other way to push the efficiency further. So I think stacked cells on silicon would be a logical progression beyond PERC. So my own research, the stacked cells, I think is one of the very important areas. I didn't have a chance to talk about it too much, but there've been some interesting ideas recently on ways of reducing the module temperature. So it turns out if you can reduce the module temperature by 5 degrees, you can probably increase the energy production of that module by 50%. So that you can make huge impact upon the costs just by increasing both the life of the module and then increasing its energy output due to the lower temperature of operation. So I think that could be a very effective way of getting to even lower costs. And then the third idea I've talked about already, solar paint. So thanks very much for your attention.